I will be taking a look at a provided Desmos graph. And if you're looking at this video without having accessed this graph yet, you should scroll down to the description of the video and you'll find a link to this companion document. You can access the Desmos calculator, or you can build a very similar one from scratch, just copying and pasting these inputs into a Desmos graphing calculator. This companion document also contains a link to the video and at the very bottom, a transcript of the audio. Let's look at everything that this graphing calculator contains, and in the process, I will teach you how to create these elements and what exactly they're doing and informing us of. So just to start, this graphing calculator can be saved to your own folder as long as you're logged in somehow. Mine is just connected to my Google address. I can save a copy to my own folder and see all my saved graphs there. You can also save it by sharing a link at any time, and it will copy all of the inputs and things that you've done to a link that will exist as long as you need it. I oftentimes do this and just email it to myself. Then I can open it and resume building that later. It's important not to copy the link from the top, because oftentimes that will lead to just a blank graph or an older version of the graph that you've been working on. You really need to use that share button. So right away, let's get into these inputs. We've got 3 folders here, and you can turn on and off the graphs or features of those folders by just clicking those left-hand circles. Sometimes we may not be looking at things perfectly as we move through these, so at any time, if you want to, you can zoom out as I did there, or use that home button to go back to essentially X from -10 to 10, and Y will show as much as can fit in that window, depending on your resolution. One thing that you'll sometimes find is that as you zoom out, you can't really see the features that you're trying to see anymore. Here in this case, X is too far zoomed out. So I've got Y where I want it. Usually I'll zoom out until I see everything in the frame. And then I will just zoom back in on only the axis that I can't really, see the details of. So we essentially want to stretch this out. What you can best do is kind of trace this and see what your X values are. Here I've got a couple intercepts there. So I'm going from 0 to 6.25. Clicking this graph settings will allow me to change that X-axis. I usually go a little bit to the left and right of what I want. I'm going to go from -1 to 11 and then just kind of move it to a good spot there. And now I can really see that whole parabola. I'll no longer be able to see the other things. This one wasn't too bad, this first parabola. However, the third one we'll want to readjust when we get there. So let's start with the first folder here. And within that folder, I'll click the arrow to expand it. I have a function that is defined f of x. I just typed that in. The exponent, you can do Shift-6, which is an up arrow, puts you in that exponent slot. Or you can use the keyboard button down here to access some additional exponents, operations, and a whole bunch of functions in there. Now the other thing that I have here is a table, and there's actually a button associated with that table. We're not going to use that in this particular video. In fact, we won't use it in my class until the very end of the quarter. You also have a zoom fit button there, which we can use to kind of centrally locate those points in that table. This table is nested in the folder. If I want to move things, the folder itself is created with the plus button here. And then if I want to move things in and out of that folder, I can sort of drag them around and you'll see that gray line show up when I'm inside it, kind of popping up to the left there. And as you create more inputs within that folder, you'll stay nested inside there. So I like the folders a lot for that feature. just adding those in early or later and dragging things in to organize. The way I added this table is right after defining that function, I clicked, instead of the plus button, which does have a table, that table won't be tied to my function. That will be a manually inputted table. Instead of doing that, I actually edit the list, and that gives me this little sneaky option to create a table that is automatically generated, and it goes from -2 to 2. You can start at any point. Say I want to start at -10, and I want to go by 2s. So I'll go -8, and then it actually will predict, as I just hit enter, it will continue that pattern along. Maybe I just want to go from -10 to 10 and then zoom that to fit that window. So that's a great tool, partly because of that zoom functionality. And we could potentially add another column and another expression to plot alongside that. Maybe we want to see how that compares to the graph of x minus 1, or just, let's say, the parent function or the toolkit function there, x squared. We can add those points in to see how that would compare. It can be very helpful looking at transformations or things like that, because you're really associating what that point was and where it got moved to. Now all of this can be hidden away, clicking that folder button. That will turn off all those plotted points, and then I can minimize that as well. Now I'm going to examine this next topic, which is looking at a function, specifically its domain and range as an algebraic concept, and then tying that in with this concept of restricting the domain, restricting the inputs, or shading. All of these are done kind of similarly. For this one, I am graphing a parabola. This is an h of t function. And so it's not immediately clear, but that will be the height of an object that is going straight up, stopping, and then dropping back down. It can also model a projectile's XY motion, so sort of like firing a cannon. However, that would be typically a little more complicated of an equation. Here we're just shooting something straight up in the air and looking at what is its height with respect to time as it goes up and down. And what I've done here is initially had this entire parabola. However, some parts of it below 0 for time, that one doesn't make sense. And then beyond this point when it lands on the ground, again, doesn't make sense. It looks like it's going down underneath the ground. So we consider that sort of like the applied domain of the problem, or the contextual domain. Sometimes that's called the practical domain. In any case, we could restrict this and only go from x, or I guess we have t equals 0, and I'm just typing a less than sign and then an equal sign, and then my other t-intercept there, 6.25. That will allow me to restrict the domain and just plot the part that makes sense. I actually could do this another way. If instead I made it an equation that contained y and x, instead of the inputs and outputs, looking at just this relationship between two variables, it will also plot the same thing. It sort of does a little calculation that instead of t, we're now doing x, but that's still going to be on the horizontal axis. And now I can actually restrict either the x or the y values. So I'm going to have y as greater than or equal to 0 within those braces. And now that will create this restriction for the y values. When you're using function notation, it will not allow you to do that in the same way because of the input-output nature of it. Now here I've also decided to go ahead and shade the range of values just to show you another feature that you have. You can use this type of shading just going from 0 to, in this case, 156.25 was the maximum. Sort of saying, let's just shade y in between that. There are some additional options with the shading. For example, you can take away the lines on the ends and just have the shaded region. Although I think if I removed the equal sign, it will make them dashed lines. So that is a little different than removing the lines altogether. Other uses of shading could be including the function itself. Here I'm going to keep that h of x. I think that it works better to use x and y instead of the t. But here, for example, I could figure out when h of x is greater than 50 or 40 or something like that. And then as I did before, I could add in a restriction, this time maybe perhaps a restriction of y. And so that would show me, the height, the region where that height is above a certain amount. I don't know, it just shows you different combinations of ways you can shade things. And of course, any other type of equation or inequality that you type in, it usually figures out what you're trying to do, and it will give you an error if not, and it will tell you what you need to fix. So now I've created a lot of edits on this one. I'm sure it's a lot different from where I started, but I can always undo back and try to get back to what I had, which was a function of t. So I think this is what I started with, was that combination there. And next we'll move on to how we graph piecewise functions as well as open and close points. This one I'm going to go back to the home -10 to 10 scaling with the x and y having a equal scaling, so we see a square axis there. And in this one there's a few different inputs going on. We can start with looking at just the line here. You'll see that if I uncheck everything, I still see labels there, so I'm going to even uncheck those. And the very first input just gives me this piecewise defined function as a line. You could definitely graph each piece of this separately using the method that I showed you before. Have several different functions or equations being graphed on restricted domains. That would achieve the same purpose. But this shows you a way that you can not only enter it all in as one thing, but you can also use the function by defining the y values with that function. Of course, I could look at these points and see that I've got -2, 3. Now for the piecewise function, we'll take a look at that. I did realize just a second ago that I had a little bit of an error in here, so it might look a tiny bit different from earlier in the video with these little points here. The reason for that was because I wanted to show you here that you can create points and use the function to input them, but I had a g of 2 twice there, and actually it shows you exactly how the piecewise function works. So let's go back a second and look at how I define this. Now you could create these multiple segments by doing 3 separate graphs, either y equals -3, y equals 2x plus 1, and y equals 3. However, instead I wanted to be able to input into the function and get outputs all with one tool. And you can even drag along that line as you click and hold down on your cursor. So it's really cool. It's very functional the way we want it to be. And the way that you input this is all embraces either y equals or a function equals. These are going to be our domains or our regions that we're plotting in terms of x, separated by then a colon and then our y output. So essentially what it's saying is for x less than or equal to -2, we want to plot y equals -3. Comma is then for x from -2 to 2, including 2, we will plot 2x plus 1. And then, now this one doesn't have x, and that's because this happens a lot in coding. If we only have one other thing to do, we'll just put that last. So we'll say, and then 3. The rest of them are y equals 3. You could also include that x greater than 2, and that would not change anything. Now the limitation of this, I'm going to turn off all these points and these labels here. The limitation of the piecewise function is it does not do a good job of showing you at the point of discontinuity, so where we have that break, which one gets the equals and which one gets the not equal. So that's what I've added in here. I've created 2 points, one at the function value, so the discontinuity is at x equal 2. I inputted a point at x equals 2, comma, g of 2. So it's evaluating the point. That one gets the closed circle, and I use the edit list option to pick what kind of symbol I want. The default is the closed circle. Next, I plot the other point, so it's going to jump down to 3. It's not going to plot at 3. It's going to start plotting as soon as we move to the right of x equals 2. Pardon me, it's not going to start plotting at x equals 2, is what I should say. So it jumps down to 3 the moment we get to the right of x equals 2. So I want to plot an endpoint there that is clearly an open circle to show we're not jumping down until we get past x equals 2. That's just labeling that discontinuity. And then I've also added x and y intercepts as an opportunity to show you how you can use labels with both words and dynamic looking numbers. Here I use the backticks around my 0, 1. I just said the y-intercept is 0.01. However, I wanted it to look like math type, so I chose to do it that way. There are a lot of other variations of how you can use these backticks. It honestly gets kind of complicated because you have to use some math type. You know, an example of that is, let's say I wanted to use the function to output this. I would have to define the function as a variable, use a variable, and then use the math type to evaluate it within that label. There's a lot of steps there, and I do cover that in another video. So check out my other videos about Desmos labeling, and you'll get into that.